So our next goal in the next few videos, perhaps, is going to be to give um, a proof of Brooks' theorem about the chromatic number of graphs. And what it says is that if you have a graph such that the maximum degree of a vertex is k, then that graph is always going to be vertex k colorable, unless the graph happens to be an odd cycle or happens to be complete. So this video is not going to contain the full proof of Brooks' theorem. Rather, we're just going to give an overview and some of the basic kinds of things that are going to be needed, some basic ingredients, namely critical graphs and some of their properties. So let's go ahead and start. So first, the statement of Brooks' theorem. It says that if you have a simple connected graph, if I forget to say all the graphs that I'll be considering are simple graphs, which is to say there are no multiple edges between vertices and no loops. In any case, if you have a simple connected graph, which is not complete and not an odd cycle, then the chromatic number of the graph is no more than the maximum degree of a vertex. And this is Brooks' theorem. The proof strategy that I'll be relating here is due to Lovac in 1973, and I'm getting my version of the proof out of a text by Bondi and Murty, the version of their book that was published in 1976. There's a modern version as well, or more recent version as well. In a nutshell, the proof goes by an argument by contradiction, saying that suppose you have a graph that didn't have this property, whose chromatic number was too big. And the idea is we take such a graph and try to find we try to find a counterexample. If we know that there is one, then we find a counterexample which was some sense as minimal as possible. So this is a common theme. I've heard it related as the minimal criminal strategy of proof. But for our purposes, what's the notion of minimality that'll be useful for us? So if somebody gives you a graph with chromatic number k, a k colorable graph, we want to say what it means for it to be k colorable, but like minimally k colorable somehow. So we call a graph k critical if the chromatic number is k, but whenever you remove an edge, the chromatic number must drop. So of course, if you think about it, if you remove all the edges, then you get something that's actually, you don't need more than one color to color it, because it's just edges that mean adjacent vertices, that force adjacent vertices to not have the same color. The fewer edges you have, the fewer conditions, the easier it becomes to color with fewer colors. At some point you remove edges, things drop down, but it's critical if you can't remove any edges without it dropping. So it must drop every time you remove an edge. Okay, so here's some examples of of three critical graphs, for example. These two graphs are three colorable, but not two colorable. You need at least two colors. You can try to start coloring it with two colors. And of course, there's only one thing I could be doing. And then, arg, I'm in trouble. And similarly with the other one, these are not colorable with two colors. But if I just go ahead and erase any one of the vertices, then certainly what I'm left over is indeed two colorable. So whenever, sorry, not a vertex, whenever I could do that, but I really wanted to say when I remove an edge, it becomes two colorable. So these are three critical graphs. They are chromatic number 3, but every time you remove an edge, its chromatic number drops down to almost 2. Okay, and if we don't want to specify k, we can just call such a graph critical. Critical just means it's k critical for some k. All right, so critical graphs have some important properties that we want to exploit. On the one hand, they are ubiquitous. If somebody gives you a k colorable graph, you can find inside of it a subgraph which is not just k colorable, but k critical. That's going to be a useful property. Another thing is that critical graphs are a restrictive class of graphs. They're special graphs. They have some nice properties. One property that I'll describe is the fact that they're blocks. So recall that a graph is called a block if it has no cut vertices. Finally, it'll be useful to us to note that they have explicit concrete descriptions for k equals 1, 2, and 3. So because these are going to be some useful properties that we'll need to be using later, let's go through each one. 1, 2, and 3, and just take a look at what these properties are and why they're true. So these three facts or properties are going to be useful for us as we go on. So let's just take a look at each one in turn and understand what those properties are and why they're true. All right. So the first property is if you have a graph whose chromatic number is k, why is there a subgraph which is k critical? Well, the proof is as follows. Consider all subgraphs such that the chromatic number of that subgraph is k. Okay. So of course there are going to be some subgraphs like that, namely the whole graph itself, but maybe there are some smaller ones. And of course the graph is finite, the finite number of vertices and edges, so there's a finite number of subgraphs. So you can pick one that has as few edges as possible among those with chromatic number k. Well, it's k critical because anything with smaller edges doesn't have chromatic number k. So therefore it'll have a smaller chromatic number and H is k critical. All right, that was easy. How about number 2? We would like to show that if you have a graph which has a cut vertex, then it's not critical. In other words, if you are critical, you can't have a cut vertex. In other words, if you are critical, then you must be a block. Okay, so suppose you have a cut vertex. Why are you not critical? Let's imagine such a graph like this. So just visually, imagining if you remove V, then we have these 3 components. These components correspond to the so-called blocks of the original graph. And what you can see is that in this picture, if these blocks are non-trivial, then, in any case, what you can see is that if each of these is k colorable, then the whole graph will be, because you can always make colorings agree by just swapping colors at the glued-in vertex V to make colorings of H1, H2, and H3 agree and give you a coloring of the whole graph. In particular, the coloring the graph G is no harder than coloring either any of these 3 of the blocks that compose G. And particularly the chromatic number of G is, well, of course it has to be at least as big as the chromatic number of the smaller bits, but it's no bigger as well, so it's the maximum of them. And in particular, the chromatic number of G is the chromatic number of HI for some I. Well, if these HIs are actually smaller than the original graph, then it's not critical because the chromatic number doesn't drop for a subgraph. So that means it's not critical. Okay. So now that we've done that, let's take a look at k critical graphs for small k. 1 critical graphs is a nice place to start. A graph having chromatic number 1 means that it's 1 colorable. Well, whenever you have an edge, you need at least 2 colors for those adjacent vertices. So to be 1 colorable, it means you have no edges. And that means that we know what the graph is. It's just a trivial graph with just a bunch of, disconnected little vertices, and that's it. Classified, done. Okay, 2 critical graphs. Well, a 2 critical graph has chromatic number 2, but whenever you remove an edge, you have chromatic number 1. But what does it mean to have chromatic number 1? It means you're trivial. Therefore, whenever you remove any edge, the resulting graph has no edges. Well, that means there was only 1 possible edge to remove. And of course, you have to have at least 1 edge because the chromatic number wasn't actually 1, it was 2 originally. If it didn't have an edge, the chromatic number would have been 1. So you have to have at least 1 edge, but you also can only have 1 edge. So you have exactly 1 edge, and the graph must look like this. So it's just a little dumbbell and a couple dots. And that's the only possibility. Now, 3 critical graphs is a slightly more fun story. So for 3 critical graphs, the chromatic number is 3, but when you remove an edge, it's 2 for any edge. What does that mean? It would be nice to have a good characterization of what it means to have chromatic number 2. So that's worth thinking about. And here's the proposition, which I've of course said slightly wrong. Chromatic number of 2 means H has no odd cycles. It really should say the chromatic number is less than or equal to 2 means you have no odd cycles, because you can have a trivial graph and that has no odd cycles. Anyways, okay. So that's the statement. So all right. I want to say if it's too colorable, then you have no odd cycles. That's really the point. And what's the proof? Well, on the one hand, if you have an odd cycle, then the chromatic number can't be no more than 2. It has to be at least 3. To color an odd cycle, you need 3 colors, because if you tried to do it with 2, you'd have to swap each time you go around, and if it's odd, you get a contradiction when you go around the circle, right? Go around the cycle. Conversely, if you have no odd cycles, then here's a way that you color it. You start with some vertex, color it pink, let's say, and then for every other vertex, you color it pink if there's a path from the starting point to it which has even length, and purple if there's a path that has odd length. And now it's an exercise that that this will always be a valid coloring so long as there are no odd cycles. All right, so now that we've done that little bit of groundwork, let's think about 3 critical graphs. So 3 critical graphs, right? Chromatic number is 3. Whenever you remove an edge, it's 2. What does that mean? Well, the chromatic number being 2 after you remove an edge means that when you remove an edge, there's no odd cycles for every edge. On the other hand, the chromatic number starts out being bigger than 2, which means that originally the graph had to have an odd cycle, right? If the original graph had no odd cycles, its chromatic number would have been 2, but it's actually 3. So to begin with, you have to have an odd cycle, but every edge must lie on this odd cycle, because once you remove any edge, you no longer have an odd cycle. So you have an odd cycle, every edge lies on that odd cycle, but that means that it's an odd cycle and that's it, because every edge is on that cycle. Well, I guess, I mean, that was assuming it's connected. I guess, you could have a graph that looked like an odd cycle and then a bunch of little things hanging off it like that. That's possible. That's possible as well. But the point is all edges lie on the odd cycle, so anything that's not there is just a disconnected vertex. All right, and that brings us to the conclusion of this video, and we will continue next time towards other ingredients of Brooks' theorem.